Hello everyone, welcome to LICD lecture 14A. Today we are going to discuss a non-inverting comparator with bonded output. Let us start. Let me just zoom in a little. Yeah. So this is my comparator with bonded output using Zener diode at the output terminals. So this is my non-inverting comparator since my sine wave is applied to the non-inverting terminal and my reference DC voltage is applied to the inverting terminal. So yeah, one difference is earlier when we have studied the comparator, non-inverting comparator, the outputs were having two states, that is plus VSAT or minus VSAT, which is automatically decided by the power supply VCC and VE. But in this circuit, we can limit or we can decide on the output amplitude. So here it goes. So here in this circuit, my output voltage levels are independent of supply voltage, which can be achieved by connecting two Zener diodes back to back at the output. So thus at the output, the limiting voltages are on the positive side we have VZ1 of this diode plus VD of the upper diode, okay, upper Zener diode. So the positive level will be at VZ1 plus VD and the negative level will be at minus VZ2 minus of VZ2 plus VD. So where VD is the diode forward voltage. So this will be my limiting voltages at the output. Now let us quickly go through the working. So your VID is V plus minus V minus. V plus is V in, V minus is V reference. Input sine wave is applied to the non-inverting terminal, that is V plus. DC reference voltage is applied to the inverting terminal, and we are comparing the two analog signals, that is V in and V reference. So these are the voltages to be compared. And right now I have one digital output with two possible states. One state is at VZ1 plus VD. Second state is at minus of VZ1 plus VD. So this is the scenario currently. My V out is AOL into V plus minus V minus, whereas V out is AOL times V in minus V reference. That is the equation of V out. Now, let us understand the working now. So whenever V in is less than V reference, okay, whenever V in is less than V reference, what will happen to this equation? This VID will be becoming less than 0. That means that this term will be negative. So my output should go to negative saturation, but it is going in negative saturation with a bounded output. So it will go to minus of VZ2 plus VD. So this is the negative level, negative voltage level. And so this will happen when V in is less than V reference. For V in greater than V reference, this equation VID will be positive. So output will switch to positive saturation with a bounded limit. So that positive voltage level is VZ1 plus VD. And the same continues for the next cycle also. So this is my inverting and non-inverting comparator with bonded output, input-output waveforms. So these are the various cases which we have described earlier. So for V in less than V reference, output will be at negative voltage level given by minus VZ1 plus VD, and it will remain at that level as long as V in is less than V reference. Similarly, when V in is greater than V reference, output will go to positive saturation with a level as plus of VZ1 plus VD. So it will remain at that level as long as V in is greater than V reference. So whenever V in is approaching V reference, what will happen is the output will switch from a negative voltage level to positive voltage level, and then from positive to negative voltage level. This is evident from here. So the first time when V in approaches equal to V reference, my output switches from negative voltage level to positive voltage level, and then again for the next time whenever V in reaches V reference, it will again change from positive voltage level to negative voltage level. Remember, your positive voltage level is this VZ1 plus VD, and the negative voltage level is minus of VZ2 plus VD. So now from the waveforms, we can conclude that the two analog voltages V in and V reference are compared. That's why this is called as a comparator. And it's also called as a voltage level detector because for the desired level of V reference, my voltage level V in is getting detected. So let us draw the transfer characteristics from the input output waveform. So this is the VTC curve for non-inverting comparator with bonded outputs. So here, whenever Vin is greater than V reference, output is at positive voltage level given by VZ1 plus VD. And whenever Vin is less than V reference, my output is at negative voltage level, which is given by minus of VZ1 plus VD. One thing to more note is that for a practical comparator, this vertical straight line, which you can see over here, it's not so straight. It's basically a slant because practical comparator will take certain amount of time to switch from one voltage level to another. That means this waveforms will exhibit a slanted edges. Okay, so that was it. Now let us go to our reflection spot. That is, we'll switch over from OneNote PDF towards LT Spice simulation and verify these concepts there. So let me just minimize this. Let me bring it over here. Okay, so now we are ready to observe the waveforms. Let me just minimize the screen also. Okay, fine. So we are now ready to move ahead in this direction. Let me minimize this so that we can view these waveforms correctly. Okay, so this is my non-inverting comparator with bonded output. We have used the op-amp as OP07 and we have applied a sine wave of 5 volts peak, 100 hertz frequency, and the V reference voltage is 2 volts. So we are comparing this sine wave this 2 volts with this 2 volts V reference. And we have connected at the output two Zener diodes back to back. The op-amp is powered with plus or minus 15 volt supply. Let's say what's the Zener voltage? Okay, so the Zener breakdown voltage is 4.7. Okay, so my let me simulate this and check my output. So here I will divide it into two plane plots. Yeah, it's okay. I can keep it in one plane also. So I can plot first V in. So V in is my sine wave with 5 volts peak. Secondly, I will plot V reference, which is a 2 volts DC. Yes, it's a 2 volts DC voltage. And finally, I will plot my output V out. Okay, so this is my output V out. Let me change the color to green. Yeah, so let us analyze these waveforms. These are the same waveforms as you can see. Let me add a plane plot and let me show you over there. Okay, so to your left hand side of your screen, we have described this in the PDF, the OneNote PDF, and on the right hand side you can see exactly it's in the same way. So we are comparing this V reference voltage with the sine wave and the output is like this. So let us see what is the output voltage now. The output is not at plus VSAT or minus VSAT. Basically it's a limited value. So negative voltage level is at minus 5.55 and the positive voltage level is at 5.55. Now let us understand this. So as you can see, the comparison is very evident uh, from the theoretical observation to your LT spice simulated values. So both are same basically. Now let us analyze how do we get that, how do we got that plus 5.55 and minus 5.55. So here we have connected two Zener diodes of a breakdown voltage 4.7. So V out is at positive voltage level of 4.7 plus the diode voltage of D2. So for positive voltage levels, we have the diode voltage, forward diode voltage of D2 and the breakdown voltage of D1, that is 0.7 plus 4.7. So the positive voltage level will be at 5.4, close to 5.4. And for the negative voltage level, we have the diode voltage, negative diode voltage for D1 and the reverse, the breakdown voltage for diode D2. So the negative level will consist of minus of 4.7 plus zero point 0.7. So that means you have a negative level at minus 5.4. So that's what we are actually getting. Let me come back with the observation table over here. Okay, so these are the values which we are getting, the V theoretical and simulated values. The output level is supposed to be 5.4 and minus 5.4, and we are getting in simulated values as 5 plus 5.55, 49 volts, and minus 5.55. The small difference is there because the exact diode voltage is not exactly 0.7. It's slightly slightly greater than this. as per the Zener diode. Okay, forward voltage. Okay, so next we will come to the live exercise. Okay, so we have to design a comparator which compares a sine wave of 5 volts peak and a DC reference voltage of -2 volts, but also the output should be limited to plus or minus 5.4 volts. So we need to select a value of Zener breakdown for as 4.7. So this is my circuit. I'm comparing a sine wave of 5 volts peak to a DC reference voltage of -2 volts. So you're supposed to plot V in, V reference and V out waveforms for the above non-inverting comparator. So I'll give you 10 seconds to think about it. Y'all can later, pause the video and try to draw the waveforms on a piece of paper and then verify the concepts. Basically, I'll show you all the solution now. Now, this is my solution. Actually, it is a little inverted. So this is my input with the reference voltage, and that's my output with the bounded positive and a negative voltage level, and that's my VTC curve. So you all can verify this, try this circuit out in LT Spice and verify the results. So we have come to an end of this lecture. We have discussed today non-inverting comparator with bonded outputs with Zener diodes connected back to back at the output. So next time we'll see another application of op-amp as a non-inverting as a non-linear applications. And that's it for today. Thank you for joining.